Good afternoon, good evening, good morning, whenever you're listening to this. I hope you're doing well and you are having or have had a nice weekend. With the last lecture, we talked about carbohydrates, and now we're going to talk about lipids. And I might ruin some foods for you today. I hope it's not too bad, but at any rate, we'll talk about lipids today. So, lipids are insoluble in water. You know, if you think of when you're making gravy or you're cleaning up something that's really fatty, it just does not mix with water. These are soluble in nonpolar solvents. So the reason they're insoluble in water is because they have a lot of carbon atoms. So just a ton of carbon atoms. So a component of lipids are fatty acids, and fatty acids are long-chain carboxylic acids. And what's the functional group in a carboxylic acid? Do you remember? Let's see. Getting ready for that final review. Okay, so that's a carboxylic acid. Now, when I say long-chain carboxylic acid, I mean 15 plus carbons. You can have 28 carbons to 40 carbons. It just depends on what type of what fatty acid you're talking about. But it's pretty remarkable how many carbons these fatty acids have. Now, they're fatty acids that can be saturated or they can be unsaturated. So saturated only contain single bonds. So we talked about that in Unit 3. Unsaturated fatty acids contain what type of bonds? They contain double bonds. Now these double bonds naturally occur as cis double bonds. You remember cis and trans, right? Of course, or you're in the process of studying for that. So a cis double bond, this would be an example of a cis double bond where you have the groups on the same side of the double bond. So you've probably heard of saturated and unsaturated when talking about fats. You know, and there's the good fat and there's the bad fat. Fatty acids are components of fats, and we'll talk about the structure of fats in just a second. So saturated typically are the bad fats. The reason these are bad is your body can't do anything with them. Your body can't make anything else from them. They don't contain any double bonds. They, have all the hydrogens that they need. So kind of a dead end for your body. So these can lead to clogging arteries. So you want to stay away from saturated fats. Whereas unsaturated fats are good fats. All this talk about fish oil, that's an unsaturated fat, unsaturated oil, triacylglycerol, which we'll get to in a second. But the reason these unsaturated fats are good for you is your body can make other molecules from these fats. So you can make cholesterol, and then cholesterol is the starting point for a lot of different steroid hormones, testosterone, estrogen, progesterone, all these different hormones. The precursor for that is cholesterol, and cholesterol can be made from unsaturated fats, can't be made from saturated fats. So, very interesting, all this stuff. So, All right, we're going to talk about the functional groups in waxes, fats, and oils. A wax, if you think about leaves and it rains and you can see droplets of water very distinctly, or on any plants or fruits, they have a wax coating, and the wax coating is an ester functional group. But if you think about this, this wax repels water, so it must contain a lot of what? Carbons. So this is an ester. It's a functional group in a wax. So we remember what an ester is, right? Okay, so that's an ester functional group. Now with the wax, we're talking about a lot of carbons. So the way these, cat's coming to help. The way you make a wax, or the way you make an ester, think, how do you make esters? So remember, it's a dehydration reaction, so you produce water. So it's a carboxylic acid plus an alcohol. The carboxylic acid that's used for a wax is a fatty acid. So a lot of carbons. And the alcohol that's used is a fatty alcohol. Again, a ton of carbons. So many carbons. I use that abbreviation R to stand for carbons. You can see it sometimes in your book, but it's used a lot in organic chemistry, so this is many carbons. Okay, so the functional group in a wax is an ester. And remember that when you make an ester, you lose water, you lose the OH from the carboxylic acid, you lose the hydrogen from the alcohol, make a really long bond. And you guys practiced that, right, for your lab exam? Yes, I hope so. And then you generate an ester. So that is a wax. All right, now a triacyl glycerol. I'm going to show you what glycerol is first. So glycerol is CH2OH, CHOH, CH2OH. So that's what glycerol looks like. Now triacyl, this means it has 3 esters coming off of it. So I'm going to draw the structure of the triacyl glycerol. Okay, so you have your glycerol backbone. Okay, so that comes from glycerol. And then you have esters. So you have your carbonyl. I'm going to put R to abbreviate for a ton of carbons. So you have 3 esters, actually. Okay, I just wanted to circle it better. So 3 esters, and then you have your glycerol backbone. So that's a triacyl glycerol. Now these R groups, these carbons, they can be the same or they can be different. So can be different. It depends on what triacyl glycerol you're talking about. So I'm going to show you a picture of a triacyl glycerol, and you'll see why I use abbreviations. Okay, so this is a triacylglycerol. So there you go. So you have a lot of carbons over here and over here. So that's why we use R. If you like to draw all of those carbons, be my guest. But you're going to need a pretty big piece of paper as well. And this is showing how the triacylglycerol is formed, that you lose water because it's an esterification reaction. Okay, so let's go back to the notes. The functional group in fats and oils, it's the same functional group. It's a triacylglycerol. So both fats and oils contain a triacylglycerol. So I'll put this at the bottom. Both fats and oils contain triacylglycerols. Now, what can you tell me about a fat? Is it a solid at room temperature or is it a liquid at room temperature? Fats are solid at room temperature. And where would you obtain a fat? Would you obtain it from a plant or an animal? So these are obtained from animal sources. You can think of lard would be an example. That's definitely a solid at room temperature. Oils, what do you know about oils? Are they solids or liquids at room temperature? They are liquids at room temperature. And they are obtained from plants. So if you think of olive oil, oops. So fats and oils both contain triacylglycerols. So that big functional group we just learned about here. The difference in the triacylglycerols, fats contain saturated fatty acids, while oils contain unsaturated fatty acids. So which is better, a fat or an oil? An oil is better for you. So an oil is good, fat is bad. Oh, no, you can't walk across the tablet. That cat's cold, apparently. Okay, so I might ruin a drink for some of you guys, but I don't know if you've ever had a cappuccino from those machines. You know, you push the button and it dispenses this yummy cappuccino, and it's just really rich and yummy. Well, those cappuccinos from those machines contain, in one serving, about 50 grams of fat. I used to drink these a lot, so I was very alarmed to find this out. So about 50 grams of fat. And, you know, so the type of fat it contains is saturated fat. The reason it contains so much saturated fat is because it's made with coconut oil. And coconut oil is kind of not a correct name for this triacylglycerol. If you look at the structure of coconut oil, high degree of saturation. So not many double bonds in coconut oil. So it is obtained from a plant, but it's a very fatty plant. Not very many double bonds there. So coconut oil, not really an oil, is not a liquid at room temperature. fact, it looks like this. So it is solid. It looks like almost like Vaseline. So if you like those cappuccinos, be careful how many you drink, because they do contain a high amount of saturated fats and just a high amount of fat in general. So it's so I was a little upset when I found that out. Okay, so moving on, we're going to learn about reactions of triacylglycerols. Whoops. Okay, so the first reaction we're going to talk about is hydrogenation. Now, we've talked about hydrogenation before in Unit 3. So hydrogenation, sorry, not hydration, is addition of hydrogen to a double bond. Now, I've just drawn a portion of a triacylglycerol. So this is part of a triacylglycerol. We would have two more of these if I had the full structure of triacylglycerol, but it's just so big it takes up a lot of space. So hydrogenation. This is used to make margarine. It's actually used in a lot of things. So if you see anything that says partially hydrogenated, this is the reaction they're talking about. So, you know, it had been known for a long time that oil was better for you than fats. So they knew that olive oil was a lot better for you than, say, butter. But, you know, as Americans, we really like to spread butter on our bread. We're not really that fond of dipping our bread in olive oil. So, when they were thinking about margarine, or in the process of making margarine, they realized that an oil, so this would be, say, from an oil is much better for you, but the problem is it's a liquid at room temperature. So by changing some of those bonds to, instead of double bonds, changing them to single bonds, you can get more of a solid instead of an oil, and that's where margarine comes from. The problem is with margarine and that partially hydrogenating step, partial hydrogenation leads to trans double bonds. Okay, Kat's got the paw on the tablet. Too bad you can't see her paw print. So partial hydrogenation leads to trans double bonds, otherwise known as trans fats. So anytime you see a label that says partially hydrogenated something or other, a lot of times it's partially hydrogenated soybean oil, it's likely that that contains trans fats. And the problem with trans fats is your body doesn't know how to deal with trans. It knows how to deal with cis, but not trans. So trans, just like saturated fats, become a dead end. And they just clog your arteries and, you know, not good to ingest these trans fats. So now, you know, with the just everywhere you see does not contain trans fats because of the scandal that has erupted once they determine that trans fats aren't good for you. A lot of food labels say does not contain trans fats. However, be careful what you're eating, because if you look at the ingredients, if it says partially hydrogenated, it does contain trans fats. One of the ways they can get around saying that they don't have trans fats is because they make the serving sizes smaller, and thereby, when it's over, I don't know if it's 0.5 grams or 1 grams of trans fats that they have to disclose, then they can get away with saying it's not there. So just be cautious. Okay, so back to this reaction, hydrogenation. When you have an oil that has unsaturation present, and you subject it to hydrogenation. So this is full hydrogenation. This is not partial that I've just been talking about. What happens is those double bonds disappear. So you're going to add hydrogen across the double bonds. So the double bonds will no longer be intact. Now the carbonyl, this is not affected. So this is not touched. So what your product looks like, CH2,7, that hasn't changed. And then you have CH. You can draw these as CH2s. I'm just going to draw them with the hydrogens explicitly shown. So the double bonds completely go away. And so we went from unsaturated up here to completely saturated. So that's hydrogenation, that's that reaction. So this is a great review from Unit 3 as well. Okay. The next reaction we're going to talk about that involves triacylglycerols is saponification. Saponification is the making of soap. So I don't know if you've ever, heard accounts. I think we did talk about this in class, where you use lye in a fat. So this reaction here is saponification. This next one is acid hydrolysis. Okay, so with saponification, you have a fat or an oil. You treat it with lye, which is sodium hydroxide or potassium hydroxide. Let's do sodium hydroxide. And what happens is those ester bonds are broken. So I pull out my scissors here. So you cleave that bond. And the glycerol gets the hydrogen. So it gets 3 hydrogens. And then the carbonyl side gets ONA. It's 3 ONAs. I'm getting crowded here. So your products from saponification, you get glycerol, and I'm going to flip this. So you have R, C double bond O, O, Na. So you get 3 of these, because you had 3 esters that you cleaved. And this is actually soap. So with soap, you have a very polar end. So this is attracted to water. And then the other end, which is just greasy carbons, that's the non-polar end. That's how it gets rid of dirt, grease, all that grime. So that's how you make soap. Okay, the other reaction that's very similar to saponification is acid hydrolysis. So instead of using base, you use acid, and you add HOH across that ester bond. So again, you get out your scissors. And this, you add the hydrogens to the glycerol, and then the carbonyl side gets the OH. So you make a carboxylic acid, make 3 carboxylic acids. So you get glycerol again, and then you have 3 carboxylic acids, or 3 fatty acids that are generated, because these contain a lot of carbons. So fatty acid, glycerol. Okay, so far we've learned the reactions that triacylglycerols can undergo. We learned hydrogenation, just went over saponification, and then acid hydrolysis. The last reaction of triacylglycerols that we're going to learn about is oxidation. And this oxidation takes place on the carbon-carbon double bonds. So it takes place here. So you would have to have a triacylglycerol that contains unsaturation in order for oxidation to occur. And you know, when you have fat or an oil, for instance, you still have some saturated and unsaturated fatty acids. So you can have a mixed triacylglycerol where maybe one is all carbon-carbon single bonds, the other one is one double bond. But it is possible for fats to contain maybe one double bond in their side chain, but they don't contain as many double bonds as, say, oils do. So fats can undergo this reaction if they have a double bond, but oils are more susceptible to this because they contain more double bonds. Okay, so let's draw out a bigger double bond. So this is in your triacylglycerol. Subjected to oxidizing conditions. You know, oxygen in the air can carry out this oxidation. So what happens is that this double bond is cleaved, and you get an aldehyde. You actually get 2 aldehydes out of this. So it keeps breaking your long chain. It makes it shorter and shorter and shorter. Now aldehydes can be oxidized further. Great practice. What can they be oxidized further to? This is unit 4. Can be oxidized further to carboxylic acids. You get 2 of those as well. Now, by the time you get to the carboxylic acid point, this is going to be a short chain. And short chain carboxylic acids stink. They really stink. Actually, one of the components of body odor is a short chain carboxylic acid. You know, that very distinct odor. So short chain carboxylic acids have a very noticeable, distinct smell. So a fat or an oil can get oxidized, and this is what we associate with being rancid. So, you know, if you have some oil in your cabinet that's been sitting around for a few years, you haven't used it, maybe it wasn't sealed very well, and you pull it out to, I don't know, make brownies or something that requires oil, one of those box kits, smell the oil. If it smells funny at all, most likely it's rancid and you don't want to cook with it. Yeah, this can happen with butter too. Butter can go rancid, so it just depends on how old it is. But there are some unsaturated chains in butter. And you can look at the labels. You know, on any nutritional label, it would tell you how much saturated fat, how much unsaturated fat something has. So, Okay, so 4 reactions we learned for triacylglycerols: hydrogenation, saponification, and oxidation. Okay, the last portion of lipids that we're going to talk about is steroid. Steroids are lipids. Now, a lot of people associate the term steroid with anabolic steroids, you know, the bodybuilding steroids, but actually steroids are the backbone for many hormones. Cholesterol is a steroid, prednisone, all these different hormones have a steroid backbone. So we're going to learn the structure of a steroid. So it's a cyclohexane ring fused to another cyclohexane ring, fused to another cyclohexane ring. It's kind of off the top right. So it's 3 6-membered rings and then 1 5-membered ring. So 3 cyclohexanes, 1 cyclopentane. So this is a steroid. This is A, this is ring A, ring B, ring C, and ring D. So there are some nice pictures in your book of steroids, and you can see how testosterone is not that different from estrogen. So no, just little tiny functional group changes, yet your body recognizes them as completely different. So that does it for lipids.